Alrighty, we got everything up? Great. Okay, next up, it's a pleasure to get to introduce a good friend, Juan Sequeda from data.world, and the role of knowledge graphs for LLM accuracy in the enterprise. I know Juan has done very much deep dive on what's the interaction between LLMs and graphs, very much our theme here today. So please join me in welcoming Juan.
Thank you. Hello, everybody. Great to be here. So I'll be talking about this paper that we published last year with my colleague Dean Ellemang. I think Dean's here, and there's Dean, and Brian Jacob, who's seen this paper and actually looked at it. Okay, we got a handful. Cool. Okay, so we're going to dive into this and actually got some special news later on. So to conclude, in case you need to leave in the next minute, investing in knowledge graphs provide higher accuracy to LLM-powered question answering systems over structured data, over SQL databases, right? So the takeaway here is, for the research that we did, that we presented here, we have evidence that we can talk about 3 times more accuracy than if you don't use knowledge graphs. You're running question answering directly over SQL databases. So the point is that I want everybody to take away is that you need to invest in knowledge graphs to be successful for your AI applications over your structured data around this. That means that you need to start treating your metadata, your semantics, your context as first-class citizens. And if you don't, you are going to fail. So don't be a failure. And a lot of this work they presented is kind of a call out that I want to make, is that we need to have more bridges between industry and academia. So I really have been very fortunate. I come from these both worlds. So a lot of the work that we're presenting here has been kind of thanks to a lot of people who have been collaborating around this. I build bridges. I like to build from industry and academia, and also I host a podcast, Cataloging Cocktails, the honest, no BS data podcast that Paco has been, that Ben has been on. We've got more folks, and today we're going to do it with Aura at 5 o'clock in room 205. You want to see it at 5 p.m. We're going to do it live. So, okay, so the research question. What we started out, so think about over a year ago, right? Everybody's doing LLMs, and people are saying, oh, I can now generate SQL for this stuff, right? It's great. And then we start seeing all these very cute examples. But what was not understood is to what extent these large language models can accurately answer enterprise questions over enterprise SQL databases. And then we're all saying in this community, oh, we need semantics, we need knowledge graphs, it's going to improve it. Okay, to what extent does that actually improve? So we don't have these numbers. We don't understand this very well. So the hypothesis is that if you actually take an LLM question answering system and you give it a SQL database, and if you take that questions over your LLM and you translate it to queries directly over your SQL database, basically text to SQL, and you compare that to questions over a knowledge graph, but that knowledge graph is the knowledge representation of that SQL database, the accuracy is going to be higher if it's over the knowledge graph representation of your SQL database. So if I were to kind of think about what a graph would look like for accuracy, it would look like this. Questions over the knowledge graph are going to be higher accuracy. And what I would love to be able to make this claim is that by investing in knowledge graphs, we're going to have higher accuracy for these question answering systems. I want evidence to support this claim. So what happens is that benchmarks, so text to SQL and natural language, I think accessing data natural language has been, I think, probably one of the inspirations for the field of computer science 60, 70 years ago. And the area of text to SQL is not new. So just call out for folks, they're thinking that they're doing the latest craziest stuff, latest coolest things. You're not. People have been working on text to SQL for decades and decades and decades. So please read that history. Now, I would argue is that the benchmarks that does text to SQL stuff are fairly academic, are disconnected from reality. So we looked at this and we said, okay, first of all, we need to have an enterprise SQL schema, and one that looks into what happens in the enterprise. So the OMG, the standards organization, has one about the insurance domain called the property casualty data model. It's open. You can go just Google it, OMG property casualty data model. You can get the SQL DDL that's there. Second, we want to understand the enterprise questions. So it's not just a laundry list of questions. There has to be a reason for the existence of these questions. And we're going to go through this quadrant of questions that we have. Now, the third thing is that we want to be able to have this context, the mapping, the semantics, make this explicit as a first-class citizen. This context was not part of existing benchmarks. So these are the three kind of the framework that we're presenting. Note that we present this benchmark, it's there, it's public, we want people to go use it, but I also want you to take away this as a framework for you to apply this in your organization. You already have your database schemas. We already had a couple of talks about that. But I want you to start organizing the questions based on the framework I'm going to tell you and make this context explicit too. So this is just the OMG standard schema right there. You can go find it, Google it. I'm just showing you a picture about it. Okay, so the questions. Think about it as this quadrant. So you have two different spectrums of complexity. One will have a spectrum of complexity of schemas. Basically, less complex schemas, less tables. More complex schemas, more tables. And then let's think about the complexity of the questions. Easy questions, harder questions. Easy questions are give me a list of things. Harder questions, metrics, calculations, KPIs. So you put these things together, you get this quadrant. So, hey, return me all the claims we have by claim number, open date, close date. Easy question over easy schema. I just need one table per 3 columns. Okay, let's increase the complexity of the question, but still something I can answer in a small amount of tables. This is about getting the average time. I need to do some aggregation, do some math. Get me the lost payment, the lost reserve, the expense payments amount, all these things. It's a list of things, and I probably have to join 6, 7 tables to go get that. Now, high schema complexity is, oh, I'm now doing KPIs, talk about total loss, about loss ratio. You need to be able to combine all of these gigantic tables and so forth. So that's the complex. So if we, in the benchmark, so let's take an example here. The benchmark has the question and the expected answer given a particular instance, not the query. Now, the reason why is, and this is something I've seen in other academic work, is that there's if you give the query, there's an overemphasis that I need to start generating the query. I don't care if you generated a query that executes very quickly. If it's wrong, I don't care, right? It's wrong. So I think if you start focusing on kind of engineering, I'm generating the right optimized query, you're pushing the focus where it shouldn't be. So for example, if I have this particular question in that particular data instance, that is the answer. So I'm just going to go through. These are all the sample questions you can see through that falls into that complexity, into that quadrant. High average time to settle a claim, right? Got to go join all these tables, do a difference between these the dates, and do an average over that, and that's a particular answer. Again, here are the types of questions that we have over this. Low question, high schema complexity. Here's interesting, like this is typical some models and databases, right? This is like that claim amount table is one table has all amounts, and then you have other tables which are like the type tables. You have to go join them to know which type it is. So you have to join all these things over and over again. Here are the sample questions. And then high question, high schema complexity. I'm joining all these particular tables together, right? And total loss, right? That's a very specific insurance metric, which is needed to be able to calculate what your loss ratio is. Every single insurance company knows what their loss ratio is. Again, these are the types of questions. So the context. We want to make the context explicit. And to be explicit, I'm talking about given the ontology, give me a schema, right? The target schema, your semantic layer. I'm using all these words very interchangeably, all right? I'm not being any pedantic around this stuff, right? And the mapping. What are the rules, the mappings that connect the source to the target? In the benchmark that we have, which is their public, we use the open standards that we're used to, which is RDF and OWL and R2RML. And as we'll talk about, other people have replicated this. I'm not saying this is only for RDF. I'm just doing something standards-based. You can do it with anything else you want, with any proprietary tool that you want to go do this. So, for example, what are these mappings? If I define the concept of a claim, I can say, hey, in the table claim, in this case, it's a one-to-one mapping. The table, every single instance, every single row in the table claim maps to the concept claim, and the company claim number column actually maps to the attribute called company claim number and so forth. So these are the mappings that happen. Then here's where we start realizing that we need to understand what this stuff means. So policy holders, how do I know what is a policy holder? Well, there's a code and it's called PH, right? And I guess you can hint why the LLMs will not know this, and that's why they're not getting accurate results. You need to go invest in this stuff, right? I need to know what a premium is. Well, to get the premium, you need to know that you have to join the policy amount table and the premium table together and put this all, right? You just need to know that's the way how to define what a premium is. So we're making this. Remember that the original claim is investing in semantics. I am investing in semantics here. Okay, we're talking about accuracy. What do we mean by accuracy? How are we scoring this? So we're actually using the term accuracy from the SPIDER benchmark. SPIDER is from the folks at Yale. They have kind of the de facto model, right? The de facto benchmark around things. What's fascinating about that is that you look at the benchmark, they're like, oh, 98%. I'm like, really? Yeah, but if you look at the tables and the questions they have, it's kind of disconnected from reality. I mean, if you look at those benchmarks, you're saying, oh, this is 98%. You're saying this is a solved problem. It's obviously not a solved problem. So there's a disconnect over there. Now, what is an execution accuracy metric is it's basically a binary decision. It's right or it's wrong. The column labels are not considered, and the order of the columns are not considered. So for example, if I say, given this question, return all the claims we have by claim number, open date, and close date, and this is the expected answer, and I get this, I generate a query that generates this result. The labels are different, the orders of the columns are different, the orders of the row are different. It's still a valid, it's still an accurate answer. However, if I get this particular answer back, generate a query that generates this answer, the claim number, you see it's 1 and 2 doesn't map, then this is an inaccurate answer. Now, LLMs are non-deterministic, right? So if I ask a question once and generates a query, I could ask it again and may generate the same query, may generate a different query. So we need to be able to go deal with this. So we have this notion of an overall execution accuracy, is that we run the question over and over and over again, and then we just divide the number of execution accuracies over the total number of runs. So if I ran the question 10 times and 10 times generated a query that generated always correct, it has 100%. If it generated 10 times and 5 times it was right, it has a 50%. And then finally, I can take all those overall execution accuracies and in a bucket, I'm saying, hey, I want to look at it for all questions or for quadrant, and I can do that average. And that's how I can get an average for every quadrant. Okay, so now the setup. We did something very, very simple on purpose because we want to understand the baseline. Second, I'll also argue that we like to over-engineer things, and we kind of think automatically believe that that simple thing is not going to work, even though we've never tested it. So first of all, this is the two kind of comparisons that we have. We have a zero-shot prompt. Literally, it's this. The following is a SQL DDL. Boom, paste it in. Write a SQL query for the following question. That's it. The following is an OWL ontology and turtle syntax. Boom, you just paste that OWL turtle syntax in there, write a Sparkle query for the following question. That is it. The results I'm going to present is using that very simple zero-shot prompt. So you can imagine that we can get even more sophisticated after these results. So with that prompt, what you see on the right side, right there, you get that question, the DDL goes into that zero-shot prompt, it generates, goes into GPT-4, which is what we tested, generates a SQL query, you execute it, get the results back. For the knowledge graph, we took the mappings and we virtualized this. So this we used data.world's virtualization. You could have materialized this into an RDF graph and just run it, but we're just using the tools that we have. So it takes a Sparkle. Note that the SQL that comes out of the virtualization, that's deterministic because that's just now part of the engine that does the Sparkle to SQL using the mappings. When the results that we presented, we ran this over a couple of weeks back in September, October. So everything has between 30 to 330 runs. So the results. This is the overall results we have. So if you take all the questions that we have, so it's around 40 questions, 10 in each quadrant, with that very simple prompt, after investing in the semantics, investing in that mapping and the ontologies, we have 54% accuracy compared to 16. That's over 3 times more. Just, again, with that very simple prompt, no vector databases, nothing, just super simple on purpose. Again, let's just try to get this very bare minimum. But we did the investment in the semantics. Now, obviously, the devil's in the details. So let's go into this. First of all, remember that you have this overall execution accuracy. So this is a heat map that shows the things that were. If I did 100 runs, like 100% meant that every single time it ran, it got it correct. Right? You can start seeing kind of these differences. Why did it get it right sometimes? Why did it get it wrong sometimes? Who knows? I don't know what's happening inside these machines, these models, right? Nobody knows. Again, what can we interpret? There's a lot of like unknowns in here, and I think that's going to be interesting to understand what's happening inside of an LLM. Now, let's look at the quadrants. So what we saw here is that this low schema to high schema complexity is 5 tables. And actually, this is pretty consistent with folks that I've been talking to at all the big database vendors, that when they're doing their co-pilots, right, their text to SQL stuff, they're really constraining it to a smaller hand of tables. Because the moment that you start increasing it, you're going to get all these hallucinations and all these things. And these co-pilots, right, people that are doing all this stuff, look, if you are a technical user and you're writing SQL query for someone who knows SQL, it's fine if it's not fully accurate, because look, the query itself is not accurate, but probably the content of that query, I don't know, 80%, whatever, is accurate, and that is better than starting from scratch. So, I mean, that's the claim, and we're going to actually see how much it's actually, these co-pilots are actually going to improve productivity. But so this is already what we're seeing, kind of from the low schema complexities. The low schema complexities, we're getting much higher accuracy already. Again, with that very simple prompt. Again, we can go see this with this map approach too. Now, what's interesting is science, right? Remember, science is a social process. Peer reviewing, get people out there, but also what is fantastic is when other people reproduce their work and validate the results. So like after we publish this, the folks at DBT, they're using semantic layers, not specifically graphs or stuff. They reproduced and validated the results. And other different semantic layer companies have been doing the same thing. You can imagine semantic layer companies, even though they don't do that much with graphs, they're now using the word graphs a lot, right? And also they're like, finally, it's our day, right? We can do this, right? So they're really, really excited about this. I think all the semantic layer companies that I'm aware of have reproduced our results. And I'm seeing things saying, oh, 99%, like, great. If you're 99%, you're doing something, because nothing is perfect in life. So, but what's interesting is to understand why things are wrong. So when we start manually looking at the results and why things are wrong, is partially accurate results I want to talk about. This is when the results are like, it's not completely wrong. It didn't get the complete exact expected answer, but it was almost there. So I kind of should have gotten some partial credit, which means like there was an overlap, like you gave me a subset of the stuff, or sometimes you gave me identifiers. So for example, these are queries that got 0 points basically, but they were kind of right? And if you actually give in a user experience, so you give this back to a user, you can say, hey, you forgot the identifier or something, give me the actual number, and then you can kind of reprompt it again. So you should have gotten some results around that. But inaccurate results, why were things completely wrong? On the SQL side, it was just hallucinating column names, right? Just making up names that didn't exist. Obviously didn't know the values, right? You had to know that this code was PH for the policyholder. Obviously didn't know that. It would use the word policyholder, and if you by chance use that term, then it could have worked, but no. And then it would just hallucinate joins. It would generate a bunch of joins that would actually work sometimes, but it would return no results, or return results, but they were wrong ones. What was fascinating is that when the Sparkle queries, when they were incorrect results, it just didn't follow the path. It went from A to C. Instead of saying the ontology says you have to go from A to B and B to C, or the edge is from A to B and it went from B to A. So it kind of got the paths mixed up. By the way, a hypothesis I have around this is that the reason why it does the knowledge graph or Sparkle, and I haven't tested myself in Cypher, but what you can tell it's also pretty well, is it's like language, right? English, subject, verb, object, node, edge, node, subject, triples. So it's kind of really, it's really very similar there. That's number one. Second is because the relationships are first-class citizens. They're very explicit in the graph. Well, in SQL databases, they're implicit. They're in the combination of these two columns, of these two tables. And third, I would argue that for when it comes to Sparkle, the variable names can be anything. So you actually give it a little bit of a liberty to be creative. So it can come up with variable names that doesn't matter. It can be whatever. So I think that's where it gives it a little bit of room to hallucinate, but it still works. Again, I don't have ways to support this, but that's kind of things that I think about. So let's look at it. These are actually questions in the generated queries given those prompts. Return all policies and their policy holders. Obviously, that was a hallucinated value. You can see here that I asked for the policy number and it returned the IRI, the identifier for the policy. So that's why it gets it incorrect. So it's a partial accurate. What is the total amount of premiums that a policyholder has paid by policy number? That was a hallucinated column. This was almost correct. Note that I asked by policyholder. The body of the query is correct. It actually includes policyholder, it just didn't project it. So this is pretty fascinating how it gets this, right? This was a simple one, right? It assumed that the claim identifier column was the actual claim number, but that's not the claim number. That's an internal primary key. What are all the premiums that have been paid by policyholders? Again, paid, that's the wrong code. That's correct. Look at this. What is the total loss of each claim by claim? That's the question. And I passed it the ontology and the turtle syntax, and it generated the right Sparkle query. This is pretty damn cool. This is when it got the direction wrong, right? So we think about policies and claims, but in reality, you have a coverage, and the claim is against the coverage, and the coverage, and you have your policy has a bunch of coverages. So that's like coverage concept in the middle. So here it went directly from the policy to the premium. So we started with this question: to what extent can the accuracy? So we have an answer. The answer, well, 16% to 54%, so 3 times more, and we get it for all these different quadrants. And kind of, if we visualize it this way, we can kind of see this extent that I'm talking about. Now, we started off with this. This is what I wanted to get to, right? This was a hypothesis. I'm presenting strong evidence to support this. So I feel very comfortable from a scientific point of view, as a scientist, to make this claim now. So we can all make this claim. I really want everybody to take away to start investing in your semantics. And for people who are struggling to get buy-in internally to why we need to invest in semantics, here's your evidence to go present it to your stakeholders. Now, one more thing. So I had the AI lab at data.world, and we're very open on the work that we're doing. We're actually a public benefit corporation, right? So as a public benefit corporation, our goal is to be able to go to share all the work that we're doing, right? We have a public benefit mission, so not only maximize shareholder value, but also support our public benefit mission. So that's why we're doing all this research, and we're presenting this all to the world. And the latest research that we've done is what we're calling on semantic query check. So this is literally first time I'm talking about this. Like, I actually did the analysis that this is stuff that Dean was doing, and I did finished the analysis on my plane last night. And I don't think, Dean, I sent a Slack to everybody like 11 p.m. last night. So you have not even, so you're seeing this for the first time, the final analysis. So ontologies to the rescue. Here it's well defined, the semantics well defined. Policy is sold by an agent, which in code, I say, there is this property called sold by, it has a domain, policy has a range agent. So if I ask a question, return all the policy that an agent sold, and the LLM generates a query like this is a syntactically correct query. It will run, it will execute, it will return 0 results. But it's semantically incorrect. Why is it incorrect? Why is it incorrect? Yeah, exactly. Because X is an agent, which is the domain of sold by, but it should be a policy. So this was the types of issues that we were seeing that the LLM was generating. So what we said is like, wait, this is semantics well defined. Basically, we're just using the RDFS inferencing rules of domain ranges, of ranges, and so forth. So this was the insight that we had is like, well, we can actually check this deterministically. So now when we talk about these co-pilots, which are like, oh, you got a question getter querying where the LLM is like the center of things, we're really moving into like the agent world, right? And by the way, everybody's talking about agents. This is not new. Agents also has been the thing for 40, 50 years in planning. So all the young folks in the audience who are thinking about agents, the latest coolest thing, please read like your old AI textbooks, because this is not new, and don't reinvent the freaking wheel. Let's advance faster. Anyways, my old man grumpy hat off now. Okay, thank you. Okay, I needed to get that out. So planning, like we could create a machine, state machines that has a plan, and one of those plans is they're going to ask LLMs to go do things. I can then check my work. I can check my work deterministically. So what we've done is that actually taken a series of all these inferencing rules of the semantics of RDFS and do a check. And we're checking the body of the rule, the body of the query, to say, does the resulting query match the semantics, the intention of the ontology? And if it doesn't, and we can check that deterministically. And if it doesn't, we know why. The domain is wrong. It contradicts. So we can actually check it. And now what's interesting is, could we actually fix it? I know why it's wrong. I can actually write an explanation. And I got this really amazing friend called LLM, GPT, whatever you want to call it. I can tell it. And I'm like, hey, this query is wrong for the following reasons. Can you please fix it? So we've checked. We have these two things. We have our semantic query checker, and we also have our LLM repair. So just, I know we got a couple minutes, I'm wrapping up here. So we've put these stuff together. And what's interesting is that now we can have accurate results. We can still have inaccurate results. And the reason why we're seeing inaccurate results is because we're checking the body of the query, not the head of the query. So maybe I'm returning some stuff in the head, which is wrong. But also I could try to repair and not decide, hey, I've tried so many times, I still don't know. So guess what? 3-valued logic, yes, no, and I don't know. And I don't know is a perfectly valid answer. So putting this together, the next question that we have is, to what extent can the ontology of the knowledge graph and the LLM itself be used to repair the errors in the Sparkle query that it generated itself? So you can actually further increase the accuracy. So we have like a series of 5-6 rules from the RDFS inferencing rules. We jumped from 54% to 72, and look how every single quadrant improved. Now, if we check the unknowns, it actually decides, I don't know, I could not fix this after 3 times, 4 times, I forget how many things we did it. So the ultimate error rate that we have right now is around 20%. And actually, for the low questions, low schema complexity, we're at an error rate of only 10%. By the way, this is still with the simplest prompt. No, nothing freaking sophisticated. Now let's go add more and make this better and better. So just to wrap up, this is just a piece of the work that we've done. We've added this inside of our new AI context engine. Like, what I'm super excited and fascinated, I can take all this stuff from our lab and our research, test this out with customers, do hackathons, and we are plugging it back into the product. So it's really, really cool. And the way that we are doing this is that the data catalog that we've talked about before is the context of your organization. And that's how we build this knowledge graph. We build the knowledge graph from all the context of all the technical and your business metadata. You have your large language models that we're combining. And together we built a series of these agents. We have the question answering agent that does all this stuff. We're working on knowledge engineering agents that can help me create the mappings. And we're doing a series of agents around this. And that is what this AI context engine is that we're doing. And I'm just super thrilled, excited that we can just take this research that we've been doing, and as actually in the opening presentation today, stand on the shoulders of giants. Folks in this community have been doing things, folks who are on that wall over here. This is all the combination of statistical and symbolic AI, right? So to conclude, invest in knowledge graphs. You want to provide higher accuracy for LLM-powered question answering systems. It's 3 times more for our previous result, but this is increasing and it's more. And knowledge graphs are a requirement for your enterprise AI. Please treat semantics knowledge with the respect it deserves. Treat it as a first-class citizen. And with that, thank you very much. Yeah, I mean, I took the liberty of going out because I got.
Yeah, we're up on lunch. Let's have a couple questions to start out with.
Yeah, great work. I read it back when you published it. Happy to see it presented with so much passion. My question is, you touched on this, but to what extent, when you give ChatGPT an ontology, it assumes that the Sparkle engine underneath will do reasoning?
Oh, at this moment, we're not.
No. The example that I saw playing with Wikidata is, okay, it knows the semantics, I mean, the basic things about the schema, properties, classes, whatever. And then when it generates queries, it assumes that you do transitive closure of type over subclass and stuff like this. And it assumes that you have done subproperties right. And the query that it generates are written as if the reasoning works underneath. So in your case, did you observe anything like that?
We did not. Well, Yeah. So to the point is that in this benchmark, the ontology doesn't have the semantics are just basically RDFS, right? So
But even there, there's not a lot of subclassing and subpropertying in this ontology to begin with, so it's not going to tickle that very easily. So we probably didn't see it because the ontology doesn't do that.
Juan, a quick one. So totally, on board and agree with you. And I know you're a big proponent of a semantics first world. So what you describe is a kind of a corrective approach. I mean, someone sometime defined the notion of a policyholder, and when they implemented it as a relational database, it ended up buried in a. So I have the impression that if instead of approaching this as a corrective action, if we build it in the process of construction, that will be a lot more efficient. What are your thoughts on that? I mean, how do we build it into the process, in the construction, so that we don't have to go and extract it and rectify the problem afterwards?
Yeah, fully agreed. I think my first answer is everybody should read Dave McCone's book on software wasteland and the data-centric revolution, right? And convince themselves to go do that. I think it's more of it's a social cultural issue to go do that. Why do we do things so ugly? Because we're incentivized, this is my rant, we're incentivized to be efficient and not resilient. You're describing a very resilient and smart world, but people are incentivized to be efficient and do things very quickly and fast. So fast is throwing shit at the wall and see what sticks and stuck, and then I jump out of my next job. So got to change those incentives. So.
Well, and this is great to see, and it's already had a pretty big impact in the large language community and the knowledge graph community within life sciences. So kudos to you guys.
Thank you.
My question is, you know the life science domain, and you know that our ontologies are a mess. How would this change potentially if I put, say, NCI thesaurus, which is not that formalized but is heavily used, right in the middle of that? What do you think's going to be the outcome there?
I'm gonna throw that.
Bashing all that fantastic work for years and years.
Yeah.
I'll take the blame for that one.
Actually, I'm going to throw that to my colleague Dean in the back.
Well, first off, things like the NCI thesaurus don't act like ontologies in the way that things like FIBO do. You understand what I mean by that, so it's kind of the wrong category. Having said that, sorry, rest of the room, we don't have much time about that, but you know what I mean. The thesaurus, you can call it a thesaurus, makes a lot more sense as if you were to treat it as a glossary. And what Juan hasn't talked about is how we go back to the data catalog and say, gee, what are the uses of compounds like glyphosate? I'm going to use Kebi because I know it by heart. So you could go into there and say, well, wait a minute, Kebi or glyphosate, that's a term. Kebi, that's a term. Now that query becomes glyphosate has use what? And the right answer is pesticide, or actually it's herbicide. So if you use it as data instead of as structure, Juan's talking about structure, and that's the problem with the OBO ontologies. Some are structural and some are data. And so the ones that are data should really be treated instead, and you even use the word as a thesaurus. When you do that, there's a whole different way to talk about it. That's not the topic of Juan's talk, but it is the topic of our product, where we actually bring the glossary in at a different phase of the story here. That's all I can say right now. We're way out of time.
To add a little bit to this, I think for the context of expand in things that we've actually done now is if you search for something like a metric, call it active users. How many active users does a company, does our company X have, right? Well, what do you define as active users? Well, maybe you have a definition in your glossary, in your data catalog. It says an active user means a user who has been to the website 2 times this, blah, 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 some formula. And it could be just in English. So what happens is that when you ask a question, part of the agent framework should say, oh, do I know all these things about this? Oh, this exists in the ontology that has a mapping. This thing doesn't exist in the ontology, but it exists in the glossary and it has this definition. Maybe I can use that to rephrase the question and let me go rephrase it back. Hey, user, I'm rephrasing this. Does this look good? Oh, yes. Try it again. Oh, now I have all those new things that showed up in the new definition that I looked up from the glossary. Those have mappings to it. I can go execute that. So that's actually something that we've already done. I mean, again, that's outside of the lab too. That's already inside of our product. And I think that is why the catalog and just like good old metadata management and glossary is critical for these things too. And then all of that would also be indexed, and that would go into a vector database. You can go find it. And what you want from the vector is to get back your identifiers, your RRIs, and that's what you're going to be using. So.
we could also talk about semantic random walks if you want to go off sidebar about this too. I think we should probably head to lunch or at least take questions offline.
Yeah, I'm here for the rest of the day, and Dean and I are gonna be around, so happy to have some.
Thank you very much, Juan.
All right.